So when you think of signal transduction, first thing I want you to think of is like second messenger system. Okay, it's extremely important and it's used all throughout the body. However, it's a topic that many nurses don't learn in nursing school. It is something that you will learn in CRNA school, but if you know it before your interview, it will set you so far apart from your competition. And at the end of the day, you want to stand out from whoever is interviewing before or after you.
Hello, future CRNA. Welcome back to CRNA School Prep Academy podcast. I'm your host, Jenny Finnell, and founder of CRNA School Prep Academy. So today we're going to talk about signal transduction. What the heck is it and why does it matter? So that's what we're going to get into. And just to kind of give you a brief overview of some changes that are coming to the podcast. So we are going to be doing this academic series. And the reason why we're doing this academic series is because now current student, he was a CRNA School Prep Academy student, David Bearden, has pointed out to me that there are gaps in the nursing education knowledge, even when it comes to interviewing for CRNA school and also as you transition into the role of being a current student. And he has identified where these gaps are. And so the concepts we're going to be talking about with David Bearden are around those concepts that he feels would be incredibly beneficial for you to not only prepare for an in-depth knowledge for your interview, but also as you transition into the role of RRNA, because these are all concepts that you will have to learn in school and are expected to know and understand. So why not get a head start? So that is why we are doing this series. And again, I'm also going to preference this with some of these topics are visual topics, meaning he does it on a whiteboard where he kind of can walk you through some of these chemical reactions and things of that nature. So I do encourage you to head over to CRNA School Prep Academy's YouTube channel, which is just CRNA School Prep Academy, and follow along there. Also, to help facilitate your learning, we will have a PDF notes for you to download in the show notes below. And this way, if you're just listening and you want to come back and hit a refresher, you will have some notes to go by. Or you can print out your notes and listen along as you look at the notes and jot down notes yourself. So that is hopefully going to facilitate. We are open to your feedback. Please, there's an email below, hello@crnaschoolprepacademy.com. Let us know how you like these episodes. Are there certain topics that you want to hear about that are in the realm of this academic, between pathophysiology, pharmacology? Let us know. Again, we want to hear from you. This is for you. So if this is not up your alley, then we want to know so we can make that change. All right. So without further ado, let's go ahead and get into the show today. Like I said, David Bearden is a current RRNA, and he also is a mentor over on Nurses Teach Nurses. If you're not familiar with Nurses Teach Nurses, it's a separate entity. It's not CRNA School Prep Academy. It's actually a separate website and everything. And it's where all nurses, of any specialty, any background, even nursing students can go onto the website and they can provide mentorship services. That could be tutoring, that could be mock interviews, resume edits, essay edits, and things of that nature, digital downloads. So again, he is a mentor on Nurses Teach Nurses. He does provide mock interviews for CRNA school on the website, and I will list to his mock interview below. He has glowing reviews for his mock interviews. So I highly encourage you to book a mock interview with David. All right. So signal transduction, what is it and why does it matter? So I'm going to be the first to tell you that this is a topic that is definitely difficult. And I give David a lot of credit for tackling it because, again, it's complicated. But it also means that it's probably not a topic that's highly touched on in nursing school. Maybe it is, but maybe it's in a very small way. And again, it's something that you should have an understanding because it really relates to how really all drugs work in the body, as well as how all different components like your endocrine system really work in your body as well. It's the cause and effect relationship between, the causation and the effect that you want to achieve. So that is why it's important. So to kind of summarize it, signal transduction refers to how cells respond to external stimuli and convert them into intracellular signals. So external stimuli and how your body converts them into intracellular signals causes a reaction in the cell, right? And I always whenever I think of signal transduction, a lot of this end result has to do with releasing things like calcium, right? So, or different chemical mediators, electrolytes of that nature that cause a chain reaction, depending on what system it's in. So this occurs, or I should say, G proteins are in a family of proteins that play a key role in signal transduction. So G proteins play a very key role in signal transduction. They act as intermediaries between cell surfaces and their receptors and intracellular signaling pathways. So again, they kind of help the cell and kind of between the extracellular and intracellular, they kind of play that role of helping convert into action. So for example, in the heart, G proteins are involved in the regulation of heart rate and contractility. Okay, specifically the G protein coupled receptors, which is abbreviated GPCR, G protein coupled receptors, and cardiac cells bind to hormones such as adrenaline and noradrenaline, which then activate G proteins. The activation leads to the production of cyclic AMP, also sometimes called CAMP, which in turn activates protein kinase A, which is also called PKA. I know you're probably like, oh my gosh, Jenny, my head's spinning already. All these abbreviations. Just take a deep breath. Like I said, there's notes in the show notes for you to download. We do have a table with all these abbreviations to get more familiar with them. And we're going to be providing kind of a little overlay screenshot of that table during the second half of this video as well. So, but again, to kind of backtrack a little bit to make sure you caught all that, the G protein coupled receptors, the GPCRs, and cardiac cells bind to hormones such as adrenaline and noradrenaline, which then activate G proteins. This activation leads to the production of cyclic AMP, CAMP, which in turn activates protein kinase A, PKA. PKA then phosphorylates various target proteins in the heart, which leads to increased heart rate and contractility. So if that painted any picture for you visually, it's a chain reaction that has multiple steps to it. And again, this is how different receptors work in your body. And it's not just, it's usually a multiple step kind of reaction. And this is a process that you're going to have to learn in anesthesia school, and something that you can learn now because it does relate to how drugs work in the body and how you get that cause and effect relationship. We're going to get into more detail on exactly what that, how that is. All right, so let's get into, in the arteries, G proteins are involved in the regulation of vascular tone. All right, so G proteins and vascular smooth muscle cells bind to hormones such as angiotensin 2 and endothelin 1. So G protein coupled receptors, again, in vascular smooth muscle cells bind to hormones such as angiotensin 2 and endothelin 1, which activate the G protein. This activation leads to the production of something called indosol triphosphate, or IP3, which in turn releases calcium from intracellular stores. The release in the intracellular calcium leads to contraction of the smooth muscle cells and decreases arterial diameter, thereby increasing vascular resistance in the blood pressure. So this causes vasoconstriction. So we just talked about how it increases contractility of the heart, how it increases the heart rate, and how it can increase your vasoconstriction or blood pressure. So start thinking about what kind of drugs do these things, because this is the process of that happening. So think about the vasopressors you use and which ones increase heart rate and blood pressure versus which ones only increase blood pressure. Start thinking about how these pathways will then differ based on which drugs those are. So certain drugs can affect G protein signaling in the heart and arteries. For example, beta blockers are drugs that block the G protein coupled receptor mediated activation of the G proteins. So, and again, just in the heart, leading to a decrease in heart rate and contractility. This makes beta blockers effective in the treatment in conditions such as hypertension and heart failure. Calcium channel blockers are another class of drug that affect G protein signaling in the arteries by blocking the influx of intracellular calcium into the smooth muscle. This then leads to relaxation of the smooth muscle in the cells, increasing arterial diameter, and decreasing vascular resistance and blood pressure. So it increases the diameter. I always think of arteries like a hose. So that's how I kind of just visualize it for myself. But again, if you're increasing the diameter, you're making the hose bigger, which again is going to make the blood pressure lower and decrease vascular resistance. Okay, so it's going to decrease the blood pressure. You're going to have a bigger hose to move through. All right, so in summary, G proteins are a crucial component of signal transduction pathways in the heart and arteries. By understanding how they work and how certain drugs affect their signaling, we can better understand what treatment modalities affect cardiovascular conditions. One other example I want to share with you guys, and something that I think is really important as far as terminology goes. So we talked a little bit about beta blockers and things of that nature. So for example, stimulation of the beta 1 adrenergic receptor in the heart results in a positive contractility, but it's also called inotropic effect. So contractility is also known as a positive inotrope. Saying terms like positive inotrope versus just increased contractility, I think shows your understanding of the pathophysiology a little bit deeper than just the surface level contractility. So jot down inotrope. That means positive or increasing. Positive inotrope is a positive contractility, if you think of it that way. Then you also have chronotropic effects, right? And chronotropic effects is where you increase your heart rate. So a positive chronotrope is something that increases your heart rate. A negative chronotrope would decrease your heart rate. Okay, and then lastly, the last key term that I want you to understand is dromotropic effect. Now, a dromotropic effect just simply increases, so a positive dromotrope increases the rate of conduction through the AV node. It speeds up that process of signaling through the AV node. Okay, that's a dromotrope. So it just takes it from one area in the heart to the other area in the heart much quicker. Now, a negative dromotrope would then slow it down. So again, these are key terms that I think you should be using when you speak about certain drugs. I think this will come across in a very positive light in your interview and really just give you a better understanding as you enter your anesthesia training. So let's review again. A positive inotrope means positive contractility. A positive chronotrope means a positive increase in your heart rate, and a positive dromotrope effect means a positive increased rate of conduction through your AV node. And again, if it was a negative effect, it would be the opposite. So whether you need to use arrows or different colors, red, green, whatever works for your brain to kind of keep those terms in the front of your brain, I encourage you to do so. All right, next we're going to go into vasopressors, since we kind of briefly touched on that. But ultimately, vasopressors are a class of drug that act on the cardiovascular system to increase blood pressure, causing vasoconstriction, which is the narrowing of the blood vessels. Vasopressors can work through various mechanisms, including the effects on the G proteins. One main G protein coupled receptor involved in the regulation of blood pressure is the alpha 1 adrenergic receptor. So a main G protein coupled receptor involved in the regulation of blood pressure is the alpha 1 adrenergic receptor. You've probably heard of that. That's a G coupled protein receptor, okay? This receptor is found on smooth muscle of cells and blood vessels and is activated by catecholamines such as adrenaline and noradrenaline, which are released by the sympathetic nervous system. So when alpha 1 adrenergic receptors are activated, they signal through G proteins to increase intracellular calcium. I feel like calcium's a repeated theme, is it not? So calcium's a very important electrolyte in our body. All right, so when levels of intracellular calcium increase, it leads to contraction and vasoconstriction. This mechanism allows vasopressors that target alpha 1 adrenergic receptors, such as phenylephrine, to increase blood pressure by constricting blood vessels. All right. So phenylephrine is an alpha 1 adrenergic receptor type of drug. So that's one of the main ways and mechanism of action that phenylephrine works. But if you dive even deeper, you're going to go into the G protein coupled receptor, right? So, and how it releases calcium. So this is how you take your knowledge and go deeper, and which is the whole point of doing these academic sessions with you. All right, let me try to find my place. I think I lost my place. Another G protein coupled receptor involved in regulation of blood pressure is vasopressin, a receptor, okay? Vasopressin, also known as antidiuretic hormone, is a peptide hormone that is released by the pituitary gland. That's really important. You should memorize that. I feel like that's always on test. So in response to low blood pressure, you do release vasopressin, or low blood volume. So low blood pressure or low blood volume, your pituitary will then release the vasopressin receptor, okay? Vasopressin acts on vasopressin receptors in blood vessels to cause vasoconstriction and increase blood pressure. Vasopressin is a receptor signals through G proteins to increase what? Intracellular calcium levels and activate various intracellular signaling pathways, which ultimately lead to vasoconstriction. Vasopressors that target vasopressin receptors, such as vasopressin, they can increase blood pressure again by causing vasoconstriction. So it's a common pathway is the G coupled protein receptors. And again, they interact with different receptors, such as the alpha adrenergic receptor and things of that nature. And a lot of them tend to release calcium, and calcium has effects both on your vascular system and your heart. So I hope this painted a brief overview. Now I'm going to let David take it away with his visual recording of this. He does talk it out. But again, if you're a visual learner, I highly encourage you to go over to the YouTube channel, which is just CRNA School Prep Academy, and watch the video there. And again, the notes also go over the video aspect of this with a kind of bullet points on the things that he talks about. So you have a nice outlined way of following along. So go ahead and go in the show notes below. You can grab the lecture notes or the study notes for this episode. And also don't forget to consider booking a mock interview with David, because again, he's excellent. You can go on Nurse Teach Nurses and read his reviews. He does almost like a study session with you with the mock interview. He will go into depth and really essentially tutor you as he reviews your mock interview and things of that nature. So if you know you have a very heavy clinical interview on coming up in your future, I do think David is going to be able to provide you an excellent experience. All right, well, I hope you guys enjoy, and I'm going to let David take it away.
As Jenny mentioned, my name is David Bearden, and we're going to talk about signal transduction. So when you think of signal transduction, first thing I want you to think of is like second messenger system. Okay, it's extremely important and it's used all throughout the body. However, it's a topic that many nurses don't learn in nursing school. It is something that you will learn in CRNA school, but if you know it before your interview, it will set you so far apart from your competition. And at the end of the day, you want to stand out from whoever is interviewing before or after you. So I like to start with the G protein coupled receptors. And I have this list right here. And this, for those that can't see, there will be a way that you can get the notes and be able to see this list of terms that I have that will explain things. And I don't want you to focus too much on knowing the names of these terms. For example, you probably should know that G protein coupled receptor is GPCR or something like that. But for example, knowing that GDP is guanosine 5 triphosphate, like that's the 5, if you ever see a 5 like there, for example, and if you go down to PIP2, you'll see that there's a 4 or 5 there, and IP3 has a 1, 4, 5. Those are more things, the numbers are more for like organic chemistry and structure and things of that nature. And it really helps for if you're drawing them out and things like that, like in an organic chemistry class or something like that. Is that important for us? No, it's just something that I put in there because sometimes people put it in there, sometimes they don't. So is it really important? No, but just for your own little knowledge, right? Some things like on here, we have adenylene cyclase. That's just an enzyme. If anything ever ends with ACE, it's probably an enzyme, right? And there's other terms on here that we're going to talk about. Sometimes I may call things CAMP or cyclic AMP, whichever. But you can always relate back to this list that I have here of terms, and this will help you, okay? When I talk about the G protein coupled receptor, that I'm going to draw right here, and it really is just it's on the plasma membrane, and it weaves in and out of it 7 times, okay? 7 times is not super important that you know that. It's not very critical, but it's just something interesting, right? Some little cool little information, right? And picture this little line that's weaving in and out of a plasma membrane 7 times. And at the top of it, there's this cup portion where a ligand or a signal can bind to, okay? And on the bottom, on the opposite side of that, you will have 3 little subunits, okay? And we're going to get more into detail on those, but just so you know, the G protein receptor has 3 subunits attached to it, okay? And then we're going to draw it out a little bigger here for us and draw this G protein coupled receptor. And I'm actually going to use some different colors here so that we can go off of this. We'll call this first subunit gamma. We'll call the second one, let's use this color. We'll go like this. We'll call this one alpha. And then we'll call this one beta, okay? And once a signal or a ligand attaches to the G protein coupled receptor and in essence turns it on, you will have this conformational change that will occur. And with these three subunits. And what basically happens is that the beta and gamma subunits will end up staying at the top near the plasma membrane. Okay, I'm going to draw a little arrow to show that we're undergoing this conformational change. And it's basically redraw the G protein coupled receptor. And you'll see that the gamma subunit will stay up top of the plasma membrane and the beta will as well too. But the alpha subunit pops off, okay? It pops off. And on that alpha subunit, the GDP will be able to convert into GTP. And then you have a GTP bound alpha subunit, okay? And it's activated. It is ready to go, okay? And again, this is definitely some advanced stuff. So if you have to rewatch it twice or re-listen to it twice, that's totally okay. Now that we have this activated alpha subunit, okay, we can get into some of the pathways that the G protein receptors can take, in essence, okay? The first one is called a GS pathway. And the S stands for stimulatory. So you can even write, if you want, stimulatory, okay? And then that's the first pathway. And that will be on the left of the screen. On the right of the screen, we will write G inhibitory. Okay. And then all the way on the right, we will write GQ. Okay. And you may be thinking, well, we have a GS, a GI, but what does the GQ stand for? And a little history lesson, it's not that important that you know this, but the Q actually doesn't stand for anything. Back in the day when they discovered it, they were trying to figure out a letter that they could use. And the earlier letters in the alphabet were already taken. And they were like, you know what, let's just put GQ. That's really just how that ended up going, okay? So now that we have this GS pathway, the G stimulatory pathway, when the alpha subunit, I'm gonna redraw the alpha subunit right here so we can see it. And remember, it has GTP bounded to it, right? And it is activated, okay? What happens is alpha subunit can, if we're going the G stimulatory pathway, it can activate something called adenylene cyclase, okay? And what does adenylene cyclase do? Well, adenylene cyclase will end up taking ATP and actually dephosphorylates it and turns it into cyclic AMP, okay? I'm gonna draw green arrows to say that we are activating or we are doing something, right? Producing it that way, right? And in cyclic AMP, that can go and activate something called protein kinase A, or PKA, right? And PKA will go on and do other things, and we'll talk about that in other videos. But PKA is very important in some instances because it will help with calcium and other parts of cells and things like that to be able to cause contractions, or you'll also see it with vasoconstriction. Actually, that is actually the GQ pathway, but regardless. I like to think that PKA, that one, whenever I think about it, I think more of the heart, and I'll write that right here, heart, for the GS pathway. That's the first thing that I think of, and I will get to that in another video. Do not fret. We're gonna get to that. Okay.
A daily dose of inspiration from a CRNA School Prep Academy student. I just got accepted to the U.S. Army Graduate Program in Anesthesia Nursing starting in 2023. Some facts about me. I've been a nurse for 8 years, the last 4.5 years in the ICU. The first 2 years of ICU was in a mixed ICU at a level 3 trauma center. They had general MICU, surgeries, head and neck, GI, open heart, working with CRRT, inner aortic balloon pumps, Impellas, and ECMO. I traveled as a MICU SICU with, of course, lots of step-down tele floating for 2 years at various level trauma centers, and then settled at a level 1 CT ICU for the last 6 months with heart and lung transplants, ECMO, LVADs, CRRT, Impella, and inner aortic balloon pumps. I did 2 medical mission trips last summer, one with IVHQ and one with One World Surgery. I highly suggest One World Surgery because I got to shadow 5 anesthesia providers between 3 ORs. One was even on the AANA board. I also attended 2 and 1 national AANA conferences. These were crucial in meeting with professors, and I was even preemptively invited to interview and had multiple invites to see their schools and shadow lectures and labs. Networking and fully immersing myself amongst SRNAs and CRNAs was amazing, and I even grew my own passion for the CRNA political community, and I just cannot wait to be an advocate. I also met Richard Wilson and Jenny Finnell, both incredibly welcoming and helpful in meeting with other professors as well. Thank you so much for everything. I know if you're listening to this right now that you know who you are, and it was so incredible meeting you. You just blew me away. The fact that you showed up to these events and you were putting yourself out there, so much to be said for that. And I'm so incredibly proud of you to start your journey into becoming a CRNA. I look forward to seeing you again at future conferences. So you guys, I shared this success story because it is full of little golden nuggets. So I really think you should stop and rewind and jot down some notes. CSPA would love to share more golden nuggets with you, so be sure to sign up for our free Future CRNA newsletter. The link is in the show notes or comments below. Cheers to your future. Now back to the show.
Now, G inhibitory pathway, the one right in the middle, okay? This one, we actually do not activate adenylate cyclase, right? It actually inhibits, okay? Because it's inhibitory, right? So I'm drawing 2 red arrows with a line through it, right? Because we're not activating adenylate cyclase. So what does that mean? We do not have ATP going and becoming cyclic AMP, right? Does not happen, right? And then we therefore do not get PKA, right? Does not happen, right? So G inhibitory, where do you see that? Well, you can actually see in the heart. The parasympathetic does it as well too. We're going to get to that, but it's that's the one that I think about when I think about the parasympathetic nervous system working on the heart, and that's what I think. Now, the GQ pathway, okay, the GQ pathway, when the alpha subunit activates that, it does not use adenylate cyclase. It actually uses something called phospholipase C. Okay, and I'm just going to write that in orange, so it stands out a little bit. Okay, and once phospholipase C is activated, it converts HIP2 into IP3 and DAG. Okay, now why is that important? Okay, why is that important? Because IP3 will go and cause calcium to be released from the SR, or the sarcoplasmic reticulum, okay? And that is important, and we will get to that later. And DAG will go on, and DAG actually activates something called protein kinase C, right? And that is important too. And when you think GQ, what I want you to think about is your arteries, okay? That's the first thing that I think about, okay? Arteries, okay? Now, there is another thing that we will get into later that comes from the GQ. It's actually called a Rho kinase pathway. So if you're really into it and you want to look it up and you want to look into things, just know that there is a Rho kinase pathway. We will get into that later. You'll see that it inhibits myosin light chain phosphatase. That's not important right now, but just in case you are somebody that looks ahead, don't fret over that. I will get into that, okay? If you're not, don't even worry about it. We will get into that later, okay? The GQ, I really want you to think arteries, okay? Take-home message for this is that you have a G protein coupled receptor that will either activate or inhibit pKa, okay? And you have a G protein receptor that will get you calcium and PKC activation. Okay, that's the take-home message, all right? And these are important for whenever you give a medication, right? Whenever you are thinking about endocrinology, okay? Endocrinology specifically, you have vasopressin, right? So vasopressin, specifically the V2 receptor and glucagon, they both work on the GS pathway. So I'm gonna write that down here. Vasopressin, the V2 receptor, and glucagon, those work the G stimulatory pathway, okay? And GQ, you have vasopressin again, but as you probably guessed it, it is the V1 receptor. And you also have angiotensin 2 in the GQ pathway. Now, I am not that familiar with angiotensin 2 as far as like a medication. I've heard that there's some places that do use it as a medication. I think as like a pressor, I don't know. My place never did that, but props to you. If you use it, cool. If not, don't even fret, okay? Now, other medications that you can use in the G stimulatory that come to mind are norepinephrine and epinephrine, right? And guess what? These norepinephrine, epinephrine, they will use a G stimulatory in the heart, right? And in the blood vessels, for example, like I ask people all the time to talk about norepinephrine and how it works in mock interviews. That's just what I do. Norepinephrine will also talk about in the arteries. It works in the arteries as well. So, but it's through the GQ pathway, okay? So this will just make you stand out in interviews. And also this is important for when you're in CRNA school as well too, because you will be learning this, and this is something that you do need to know, okay?
Well, that wraps it up. Thank you guys so much for tuning in. And I hope you guys found that helpful. I would love to hear from you. So don't forget, you can go ahead and send us an email at hello@crnaschoolprepacademy.com to let us know what you thought. And be sure to grab your study notes in the show notes below. And just so you guys know, this is part 1 of at least a part 2 series. So we may break it up even into a part 3 series, depending on the length of the part 2. So there are more concepts to come around this topic. So stay tuned. And thank you so very much for tuning in. I appreciate you. We'll see you next week. Cheers to your future.
Hey, future CRNA, as always, I appreciate you and your loyalty. Thank you so very much for tuning in this week. I'd love to hear from you, so screenshot this episode and share it to your IG stories with your biggest takeaway. Don't forget to tag me at CRNA School Prep Academy so I can personally thank you. Be sure to head over to CRNASchoolPrepAcademy.com to check out our blog and gather free resources to help you along your CRNA journey. Stay strong, and I'll see you next week.